This one has a similar feel to the last problem. A ball is launched vertically upward with height in feet given by this h of t equals 60t minus 16t squared after t seconds. Okay, what are they going to ask us? At what time does the ball reach its maximum height? Okay, let's think about it. So this graph here, we've got a quadratic, so we know the graph is a parabola. I went ahead and drew just a sketch of what that might look like. Now the ball, if you were watching it, the ball just goes straight up and straight back down. But if we graph it with respect to time, then it kind of curves out that way like the parabola, right? So we're thinking, okay, when does the ball reach the maximum height, right? The vertex. We learned to do this stuff way back in algebra, right? I mean, we would need to find the vertex of the parabola. But we could also use calculus to find that point. And I would argue calculus is going to be a faster approach to find the vertex. What's going on at the maximum height when you think about calculus, right? So we know this is really, we call it the height, but that's really the position. The derivative would be velocity. Hey, if you're at the very top, if imagine that ball flying up in the air, what happens to the ball at the very, very top of its arc? It pauses just for an instant, right? It pauses before it starts coming back down, just like that particle on the line would move directions, and it has to stop for an instant before it goes back the other way. You could also think, hey, if you're at the top, the vertex, isn't the slope of the tangent line there 0? You could think of it that way. That'd be true. Okay, in any case, the maximum height occurs when the velocity equals 0. So we need to find the velocity function, set it equal to 0, and solve. Okay, I've got that on the next page. Here it is, the height at time t. I'm just repeating this, 60t minus 16t squared. So hey, taking a derivative, oh, I love that, just a polynomial. Velocity v of t equals 60 minus 32t. And if we set that equal to 0 and solve for t, well, we can subtract 60, divide by negative 32, and you might think of it as the fraction 15 over 8 when you reduce. Or in this case, using a decimal is perfectly fine since you don't have to round. You might think of it as t equals 1.875 seconds. So not quite 2 seconds before it reaches the top of its arc. That's a long time, actually, to be flying upwards. Okay, so that's the time when it reaches the maximum height. What else might we ask? Well, if that's the time of the maximum height, what is the maximum height? What is? How high up does it get? Well, here we don't need any calculus, right? If we know the time that it takes to get there, then we can just go back to h of t and plug that time in. So I'll use the decimal here, h of 1.875, and you can see I'm plugging it into the original function. And a couple clicks later, I got 52.25, and that is feet. That's pretty high up there. I don't know, somebody to throw something vertically, it's not easy to get 50 feet. That's pretty good. Okay. We just have one more question, but it's definitely different. You're gonna see other scenarios, kind of like this one with the ball, but in different contexts. So they get pretty creative. Okay. This last example is very different from the others. It's much, much, much more conceptually based. I'll try and not reveal any part of the answer there. Okay. I'll read it together. In a factory, the average productivity of all employees is denoted A of X, where X is the number of workers. So you think, from all the people working in a given shift, take all of the productivity that all of those people did together and then divide it, essentially divide it by the number of workers, and that would be the average productivity. Okay. And we're just going to call that A of X. Okay. If A prime of X is greater than 0, should the company hire more workers or let some go? So let's see. This represents the rate of change in the average productivity. Okay. If that's positive, greater than 0, what do we do? And kind of the dilemma is, if if we're thinking average productivity, we want the average productivity to be as high as possible, right, in our factory. So if we hire more workers, there's no question more work is going to get done. But then there's more workers. So it could be that more work gets done, but the average productivity goes down, right? And then that's not that's not cost efficient, right? Or on the other side, if you let some workers go, productivity is going to go down. But maybe it's worth it in the end because, you're getting a better bang for your buck, if you will, if you let the right people go. You just keep the more productive people. The average goes up. Okay, I think you understand. So it's based on this, right? So if the rate of change is positive, I think, let's see. Okay, I can just reveal this. What can we get out of that? Well, we don't know a whole lot, so we'll just start here. So if that is positive, then that means the slope, and I'm referring to the slope of a tangent line, the slope of the original function is positive, right? If the derivative is positive, that means the slope is positive. And I think at this point, I was running out of space on my page, so I've got the whole answer here. I'm going to try and cover up the answer and just show you my graph. Okay. So what is this? So the slope is positive. If the slope of the original is positive, that means it's going up, right? Okay, so I got this quick little graph, average productivity here, and the number of workers here. And, I drew this curve kind of going this way, but it could have been a straight line, it could even curve the other direction like this. I just happened to draw it that way. All right, so let's think about it. I know it's positive whatever it's doing. So imagine I have X workers. Okay, so if I bring this point up maybe about right there, if I have my X workers, this is where the average productivity is. So should I hire more workers or should I let some go? Would average productivity go up if X goes up, or would average productivity go up if X goes down? And in this case, I want to move this over because this slope is positive. I know if I move to the right, it's going to go up further. So if I move over this way, then this is going to go here. So I want my number of workers to increase. And not only will that increase just the productivity, period, it will actually increase the average productivity. So not only do I get more done, but actually each person gets more done because I hired more people. And that seems kind of strange maybe, but it certainly be the case. If you bring more people in, sometimes that alleviates some of the maybe more like mundane tasks, and then those people can focus on other things, or who knows what, maybe then you can say, okay, now you only do this one job, and you over here you only do this one job, and they end up being way more productive that way. Okay, in the end, we want to hire in this situation, get X to be further up, because that's going to mean our average productivity goes up. Everybody's going to get more done. So you think like, how could this change? Well, if this was negative, then the slope would be going down this way, and we'd actually want to let some people go, because then average productivity would go up, um, in that sense. But here, hey, we want to hire more. Okay, that's all I've got to say about 3.7. Go check out the homework. You're gonna see other examples, some examples that are similar to the ones we've done, other ones that are, they've got a maybe like the same feel, but they're definitely a different context. Check it out.